Swayam Prabha. Digital India. Educated India.
So, this class I will start one new topic, that is beams on elastic foundation. So, in my previous lectures I have discussed about the bearing capacity and settlement of shallow foundation, and during my discussion as we have seen that we have not taken the foundation soil interaction, because that means we have taken the foundation is a separate part and the soil is a separate part in most of the cases. So, we have not considered the foundation soil interaction. So, now this in this topic we will consider the foundation and the soil interaction, and then as well as the another aspect is that in the previous problems we have taken the settlement and bearing capacity, but the shear force and the bending moment, those are also required to know during the design of a foundation. So, then how we can determine the settlement and the bearing capacity and the shear force of a foundation by considering the soil and foundation interaction, that will be discussed in this topic. So, in this topic in this section I will concentrate only on the shallow foundation part, but during my discussion on pile foundation, there also I will discuss how this beams and elastic foundation concept can be used to analyze the pile foundation or determine the settlement of the pile foundation, specifically for lateral loaded pile. So, now the soil foundation interaction, it says that analysis of interaction between structural elements such as beams and plates on infinite and finite extent resting on idealized deformable media. That means, soil will be replaced by some mechanical elements, and we will consider structural element either beams or plates, but in this course we will concentrate only on beam. So, plate part will not be discussed, but that can be also considered for model the foundation, and that beam can be beam or plate can be infinite or finite both, and I will discuss when you will use the infinite plate or beam, when you use the finite beam. So, these interaction problems can be useful for isolated footing, design of isolated footing, combined footing, raft foundation, pile foundation, and transportation system like pavement, railway tracks, then your airport runway. So, those can be modeled by using these interaction techniques. Now, the idealization of supporting soil media is usually represented by mechanical or mathematical model or the numerical model. So, here we will consider on this mechanical part, that means the soil will be idealized by different mechanical components like spring, dashpot or both, and then foundation will be idealized either by beam or plates, and then we will consider the interaction between this beam with those mechanical elements, and then this beam can be infinite or finite depending upon which type of problem we are solving. So, now first I will discuss the first idealized model, that is the Winkler model. So, Winkler model basically consists of a system of mutually independent, discrete, linearly elastic spring. So, that means the soil is model with spring. So, this is the soil, so which will be model by spring. So, this soil layer is modeled by a spring whose spring constant is K. So, these are model with spring constant K. Okay. So, now in this Winkler model, the soil is replaced with the spring and the soil is basically idealized by the springs whose spring constant is K, but these springs are not connected to each other, they are discrete and this spring constant is linear, or that means a linearly elastic model. And then this deformation of the soil media at any point on the surface is directly proportional to the stress applied on that particular point, and it is independent of the stress applied to the other location. For example, suppose in this middle spring, if I consider this middle spring will deform due to the load or stress applied on this middle spring only, because as there is no connection between these springs, even if you apply the stress or the load any other spring, so that spring will deform, but due to the stress applied to the other spring, the middle spring will not be deformed. So, middle spring or any spring will deform due to the stress applied on that particular spring. That means the deformation of that any particular spring will not influence due to the stress applied to the other spring. Clear? So, that means if I apply a load in this particular spring, so only this particular spring will deform, other spring will not deform at all. So, this I can say that this is the middle spring where the P is applied. So, these spring will only deform, the other spring will not deform at all, they will remain same, because your stress is applied on a particular spring and these springs are not connected. And this deformation is also linear. Okay? So, that means as you increase the stress, your deformation will increase. So, I can write for a Q or U case the same. If your stress is applied over a certain springs, that means this is the stress and those are applied over number of springs, then those springs will only be deformed. So, this is the your stress is applied on these 3 springs. So, only these 3 springs will deform, other springs will not deform. Okay? So, this is the Winkler model. So, as I mentioned, the deformation of the spring is proportional to the stress applied. So, that means if you apply the stress, so deformation is W. So, that is K times of the W, where K is the spring constant, or here it is mentioned that this K is the modulus of subgrade reaction. Or it is simply called subgrade modulus. So, if it is if the stress is acting over a rectangular area, that means the xy plane, then q xy will be equal to k time of w xy. So, that means it is acting over a rectangular area. So, that means it is given that it is these springs are not connected. So, stress applied on a spring will not influence the deformation to any other spring. So, that any spring will deform due to the stress applied on that particular spring. So, other spring will not be influenced because of the stress applied to any spring. So, now how I will calculate the subgrade modulus? So, that is one problem. So, we know the stress, and if you know the K value, then you will get the deformation, okay, of the soil. So, now this determination of subgrade modulus can be done by plate load test. So, plate load test I have discussed. So, in the plate load test I will get the settlement versus pressure, or load versus settlement plot, or pressure versus settlement plot. So, this is the pressure versus settlement plot, and we will determine the K value corresponding to the stress which is applied. So, that means the K is equal to the stress at 1.25 millimeter. So, it is the stress divided by a particular settlement. So, you can see the ratio of the load per unit area of horizontal surface of a mass of soil to corresponding settlement of the surface. To determine the slope of the line joining between the plane corresponding to 0 line, 0 settlement, and the point of 1.25 settlement of a load settlement curve obtained from a plate load test on the soil using 75 centimeter diameter or smaller diameter, but not less than 30 centimeter, with correction of the loading plate with corrections of the size of plate. So, as per IS code, this is the definition of the K. So, I will or is most of the cases this is the definition, but few researchers have suggested some different settlement value corresponding to that value we have to determine the subgrade modulus. In some cases, one particular stress is recommended, that you calculate the settlement for a particular stress, then you divide that settlement with that stress, that is also K value. Sometimes the stress is defined or taken and corresponding settlement is calculated, or sometimes the corresponding a particular settlement you have to calculate the stress, but the definition is stress or and divided by that particular settlement. So, but here most common definition is stress corresponding to 1.25 millimeter settlement divided by 1.25 millimeter. So, that means if your stress is in kilonewton per meter square, so this unit of K will be kilonewton per meter square, and here it is mm per mm. Or if your Q is in kg per centimeter square, so this definition as per this definition, this will be Q divided by 0.125. So, this is in centimeter. So, this unit will be kg per centimeter square divided by centimeter, or sometime it is called kg per centimeter cube also, but I would prefer to represent this is kg per centimeter square per centimeter. Okay. Now, ultimately you have to convert it, and then you have to represent it in SI unit, kilonewton per meter square per meter. So, this is the unit of K subgrade modulus, that means the kilonewton per meter square per meter, okay, because this Q is the stress, and that I will get from this chart. Now, I want to mention that this red one is the original chart. Okay. So, red one is the original plot of stress versus settlement. So, you can see that this red one is not a straight line. So, to determine the subgrade modulus, so what we have to do? We have to consider a 1.25 millimeter settlement. Okay. Then the corresponding point on the settlement curve, you join that point and the 0 point and draw a line. So, that black line is basically join this point corresponding to 1.25 settlement millimeters settlement and the 0 line, and then you join. Okay? And then the line, basically this slope of this line will give you this k value. Okay? So, that means corresponding q you calculate on that straight line, and then you determine the k value. That means here this k is basically a second modulus. That means you are joining a particular point corresponding to 1.25 millimeter, and then joining the 0 point and then that point, and basically the slope of that straight line will give you the k value. Okay. So, that means here this k is q divided by 1.25. So, that means you just calculate this q corresponding to 1.25 millimeter settlement. That means on the curve you go to this point, if it is not straight line you make a straight line, and then you get the value, okay, corresponding to that 1.25 settlement. This is my q value. Okay. And as I mentioned that if when you do the plate load test, you do the test for either in between 30 centimeter to 75 centimeter diameter plate, and do not take a plate size less than 30 centimeter, and after 75 centimeter diameter plate not much variation of the value is observed. So, it is recommended you take 75 centimeter diameter of plate, but you can take smaller size of 75 centimeter diameter plate, but if you take the smaller size of the plate, then you have to apply some size corrections. So, what are those corrections? So, there are number of corrections you have to apply once you get the k value. So, that corrections are size of plate, shapes of plate, and the depth of plate. So, these are the three corrections generally we have to apply. So, Tazaki suggested in 1955 that for the sandy soil, this k is the modulus that you want to determine for any plate size or foundation. Okay? And K1 is the modulus of subgrade reaction that you have determined for a particular plate. Okay. Suppose your plate size is here, the Tazaki has taken 30 centimeter plate size, that is 30 centimeter or 0.305 meter plate size. So, this K1 value is calculated or determined by using a plate load test where dimension of the plate is 30 centimeter. So, that is K1, and B is any plate dimension obviously greater than 30 centimeter here, because 30 centimeter is the lowest press size, or any foundation also, and then you use these correlations to get the k value for the sandy soil, and use the second correlation to get the k value for the clayey soil, specifically for the steep clay. Okay. So, suppose if you want to determine the k value for 75 centimeter plate, and you have done the test for using 30 centimeter plate. So, that means you get the K1 which is corresponding to 30 centimeter plate. Now, your B value will be in that case 0.75 centimeter, and the B1 value will be 30 centimeter, and again B value will be 75 centimeter. Then you will get the subgrade modulus. So, that subgrade modulus will give you corresponding to 75 centimeter plate. And remember that by using these expression also you can see that as your size of the plate increases, the subgrade modulus value decreases. So, that is why we have to take the plate size as much as big possible. Okay. And it is mentioned that why it 75 centimeter is suggested by IS code, that it is observed that after 75 centimeter, if you further increase the plate size, so that not much variation in your result is observed. but those limitations are still there. I mean, I have discussed those limitations, that if the soil is a layered soil, if it is not a homogeneous soil, then also you have to use these data with some caution. Then if it is unsaturated soil, that means that capillary rise may be possible, and clay soil, this is a short term test, and clay soil, it is a long term behavior. So then also you have to use them with some cautions. So those limitations that I have discussed will still be applicable here also. Okay. And then the shape of the plate. Suppose if you are doing the test for square plate, then it is fine, because these expressions are all valid for the square plate. I mean, these k value you are getting for the square plate, but but your actual foundation is a rectangular foundation. Then how you convert that value for the rectangular foundation? So first step is that you have done the test for K1 equal to say some plate size B, then you convert it for the actual foundation if it is a rectangular footing by using these expression, and that is for the clay soil or medium dense soil. So more or less for any kind of soil I can use these expressions. So remember that suppose you have done the test on a very say 30 centimeter plate, and you want to determine what would be the bearing capacity for a 1 meter foundation, 1 meter by 2 meter foundation. So first you convert 30 centimeter to 1 meter. Okay. So that means here it is observe the after 75 centimeter not much variation is there, but still there will be some variation, but the rate of variation will decrease if your plate size or the foundation size is beyond 75 centimeter. So it means that you can say that it will be always better if you do the test for a real foundation dimension. Okay. But here it is very difficult to conduct a field test with real dimension, that we are that's why you are going for a plate load test. Okay. And then it is observed that 75 centimeter is a number after which not much variation is observed in your this plate load test data, but still there will be some variation. So now if you go for real dimension of the foundation, then you can use these theoretical values, because theoretical data, theoretical equations are available. You can get the subgrade modulus for any foundation. So that means if you want to suppose determine the what would be the foundation or bearing subgrade modulus for 1 meter cross 2 meter foundation. So in such case you have done the test for 30 centimeter plate, then first you convert it to the 1 meter cross 1 meter plate or foundation by using this size of plate equation. So that means first this is your measured k value, because you have done a test K1 corresponding to your 0.3 meter plate, and you want to determine the clay for a 1 meter cross 2 meter foundation. Then what you will do? The first you K1 you convert it to K for 1 cross 1 meter square foundation by using these equations. It can be if it is clay or the sand. Once you get the K, then you or K dash, then you convert this K dash to K for 1 cross 2 meter square foundation by using these expression. Okay. So first you convert the K1 to K dash to get the bearing subgrade modulus for 1 meter to 1 meter foundation, but in both the cases this is square. But if your foundation is 1 meter cross 1 meter, then fine, that is your actual or the required subgrade modulus, but your foundation is 1 meter cross 2 meter, then you use the second conversion. Now you convert this square foundation to rectangular foundation. So in such case In this case, for the first conversion, your B will be 1 meter and B1 will be 0.3 meter, and your second conversion, B will be 1 meter and L will be 2 meter. Okay? So, this is your conversion for plate size and shape. Now, the third thing is the depth of the plate. Now, ideally your depth of foundation and plate depth should be same. If both are same, then no correction is required. But suppose you have done the test on a surface of a soil and you have placed the foundation at a certain depth, then you have to apply the depth correction. So, how we will do that? So, this is the correction factor, and remember that for the clay soil, depth is not an important parameter for subgrade modulus. That means, whether you do the test on the surface or at a depth, so this value will not be significantly changed. But for the sandy soil or granulous soil, your modulus of elasticity increases linearly with depth. So, that is why K has a very important effect with respect to depth for granulous soil. That means, for clay soil depth correction is not required, but for cohesionless soil this depth correction is required. So, in case of K may be assumed to be independent of depth. So, it is mentioned for the cohesive soil. So, how we will use this conversion, and D is the depth of the foundation, B is the width of the foundation. So, again suppose now there is a 3 cases. Now, you have done a plate load test with 30 meter plate, 30 centimeter plate, and plate is resting on the surface, and you have now want to determine the subgrade modulus for a 1/2 meter foundation which is resting at a depth of 1 meter. So, what you will do? So, first you convert the K1, this K1 you convert it to K dash. Okay? So, first it is for 30 centimeter or 0.3 meter plate. Now, you convert it to for 1 cross 1 meter square foundation. Then you can convert it to 1 cross 1 meter foundation. Okay? Then you can convert it to K double dash, that is for 1 cross 2 meter square foundation. Then you convert it for a foundation. Here all the 3 cases are surface foundation. Okay? Then you final K, that will be 1 cross 2 meter square with df is equal to 1 meter, and this all these cases df or dp, this will be dp is 0, here also df is 0, here also df is 0. So, you understand that the conversion part, that dp is equal to 0. That means, first you convert it for the square footing, from plate load size to square footing, then the rectangular footing, then with some depth, and then you can this third and fourth K value you can interchange. That means, you can do first depth correction, then go for the shape correction, that is okay, fine, but you have to first convert it to square footing. But that means, first from plate you have to convert it to square footing, okay, or any other plate size. Suppose you have done a test on 30 centimeter plate. Now, you want to convert all these things for 75 centimeters plate, that means 75 centimeter square, that means 75 centimeter square plate. Then do the same thing. That means, in such case you convert the 30 centimeter plate load test data to 75 centimeter first, then you apply the depth correction. Okay? So, this is the technique by which you can apply 3 different corrections: shape, size of the plate, shape of the plate, and depth, embedded depth of the plate. And if you want to combine effect of size and depth correction, combine effect, then this is, because this case it is a combined effect. because we have first gone to size and depth. Suppose if you, this is your size correction, this is shape correction, and this is depth correction. So, if you do these two together, okay, if you are applying these two together, if you are doing shape and size correction at a time, no issue. But if you are using the size and the depth correction at a time, then this condition, that means this is your depth correction and this is your size correction. First part is your size correction, that means you have to convert first to square footing, then you are going for the depth correction. Okay? And when you are doing that, remember that you have to satisfy this condition. Okay? That means this size correction and the depth correction, this part should not be more than 2 times of K1 b plus b1 divided by 2b whole square. That means if you are applying these two corrections combinedly, that means this part should not be greater than 2. Okay? So, this part should not be, if it is greater than 2, you consider twice 2. Okay? So, this is the thing, that means this part, this second part should not be greater than 2. So, once you get this corrected value, that means k you have corrected with respect to size and the depth. So, that means you remember that the depth correction factor should not be greater than 2. So, when we apply the depth correction factor, because of this depth correction, because as I mentioned, as your size of the plate increases, your subgrade modulus decreases, but as your depth increases, your subgrade modulus increases because of this depth effect. But you have to restrict that for any condition these values, that means it will not increase twice, 2 times, more than 2 times. Okay? That means this due to depth correction, your subgrade modulus value should not increase more than 2 times. Okay? So, that you have to restrict this. So, that means here first you do the shape corrections and then the depth correction at a time, but you restrict this thing within 2 or equal to 2. Then once you get this value, then you can apply the shape corrections also, if it is a rectangular footing. Okay? So, that means you can go in this sequence also, that means k to k dash to k double dash to k, but remember that when you are applying these depth corrections, if this correction or correction factor is coming more than 2, you restrict it to up to 2. Otherwise, this sequence also you can use, okay? But it should not be more than 2. Okay? So, that you have to remember. Otherwise, you can go with this sequence. So, next we have different other correlations also, and in the next class what I will do, I will give you some more correlations by which you can get the k value, and I will discuss some other methods also by which you can determine the k value, and then I will give some ranges by which also you will get the k value for different types of soil. Thank you.